Hi everyone, in this section we're going to work on some three-dimensional geometry. So you should have formulas on your sheet, but I'm going to run through them really quickly anyways because I think there's some things I want to say about a couple of them. So for a cube, we need to be able to find the volume and the surface area. To get the volume, you need to multiply basically length times width times height. But each of those is the same, so that's really just s times s times s, which is s cubed. And this immediately brings me to one of the things that I want to say. You can see that the box, the next shape over, is called a rectangular prism. Really, a cube and a cylinder are also prisms. So I would say in general, it is worth remembering that to find the volume of a prism, you need to find the area of the base, and you need to multiply it by the height. So when I look at this cube, I could think about it as the base is this bottom square, and really all I've done to make volume is take that base and stretch it up. So this would be like my height. So the area of the base is s squared, and you multiply by the height. And a nice thing about this is it turns it into just your two-dimensional geometry formulas multiplied by height, and hopefully that feels like less to memorize. So similarly for the rectangular box, and you can think about this different ways, but easily here I could say, okay, the volume is going to be area of the base, which is length times width, and then I just need to multiply that by how tall it got stretched up. So length times width times height. And for the cylinder, the base is a circle, so the area of the base is pi r squared, and then I just need to multiply by how much I stretch that out, and that's h. So you could do the same thing with a triangular prism, where the base was a triangle and you just stretched it out and gave it some height. Really, any shape you think of. If you make a trapezoid for your base and stretch it out, this would work. For surface area, some 3D shapes, it's complicated and not obvious at all. But some of them, it's actually fairly simple if you, again, go back to your two-dimensional shapes. So for a cube, notice that every face of this cube is an identical square. So s squared is the area of every single face. And there are 6 of them. So the surface area, which sometimes I give an SA, a lot of times I just see people use an A for it because it is an area, whatever you like is fine, is s squared plus s squared plus s squared, 6 of those, so 6s squared. So I don't want that to feel like memorization, but I think that's something you should be able to reproduce. You should be able to figure that out without having to memorize like 20 geometry formulas. Same idea with the rectangular prism. If I look at this, I'm going to erase my lines. The front face is W by H. The side face is L times H. And then the top of the box is W times H. And then we just need to recognize that there are 2 of each of those. So the surface area is going to be 2 times WH plus 2 times, oh, I wrote WH twice. What was I doing? On the top, it should be WL. WL plus 2 times LH. So again, I expect that you can figure this out. I don't really want you to have to memorize all these formulas. I just want you to be able to think through the shape that you have here. And then the last one where I'd like you to be able to figure out the surface area is the cylinder, which I don't think immediately looks as easy. We do have a pi r squared on the bottom and another pi r squared at the top. So that part is not so bad, but the outside is maybe a little tricky. So I have this diagram at the bottom to show you how to visualize that. And this is the deal. You're going to basically peel off the top and bottom circles. We've already thought about those. And then you want to imagine, what if I took that outside hollow tube that's left over and sliced and unrolled it? And the answer is you would just get a rectangle. And the rectangle would be h units tall. But we can also figure out the width. The width is the distance around the circle. So the width of the rectangle is really just the circumference of the circle, which is 2 pi r. So the area of that outside rectangle that's rolled up is 2 pi r h. I know that one's harder, but I would work on it, try and get that one in your knowledge base. It's one that'll come up again in pre-calculus, and especially Calc 2, we use a ton of cylinders, but Calc 1 as well. So the surface area for that is 2 pi r squared. So that's the top and the bottom. And then a 2 pi r h. That 2 is not because there's 2 of the outside, it's because the circumference is a 2 pi r. All right, so those are formulas that I would like you to be able to have memorized or come up with off the top of your head as needed. I think we'll also occasionally see some cone or sphere references. I don't need you to memorize those. I'll either provide those, or if you need to go look them up, that's fine. But just to get them written down, the volume of a cone, interestingly, is just 1/3 of the cylinder that it would fit inside of perfectly. So it's 1/3 of a pi r squared h. And then surface area, I'm actually spacing on right now. I think it's on your sheet, but I'm not even going to write it down because I don't know that that ever comes up in this class. For a sphere, the volume is 4/3 pi r cubed. And that's one where I don't think it's obvious at all where that comes from. But that's one of the cool things that we do in Calc 2 is we actually build up those formulas from scratch. I don't know that that's how they originally came up with them, but it's a cool way to justify them for yourselves. And then this one I do remember for reasons that I'll tell you if you take calculus from me. This is 4 pi r squared. So again, I think these are all marked down on your geometry cheat sheet. I just want to emphasize that I don't need you to memorize anything about a cone or a sphere. If you remember that the volume is 1/3 of the cylinder, that kind of helps me remember, but it's not a big deal. Okay, hopefully this doesn't make this one too long, but I want to just jump right in here and do my examples rather than cutting and doing a separate video. So I think what makes these a little more interesting again is having some composite shapes, so you have to think about it a little bit more. I don't think they're terribly complicated in your homework, but here's an example. We can take 2 rectangular boxes and stick them together. And the volume, at least, is fairly straightforward. We can just look at them entirely separately and say, okay, so this first one has volume equal to length times width times height. The length is 72 inches. That's given down here. The width, I'm going to call that I don't even know. I'm going to call that the 24 inches. And the height I will call the 12 inches. These are all totally interchangeable. Whatever your perspective is, you can call anything length, width, or height. And then this just becomes a quick crunch. And I got 20,736. These were all inches. So either because we know the units of volume should be cubic, or because we see that we're multiplying inches by inches by inches, we should get that our units are cubic inches. I'm going to call that V1. V2, use a little subscript there to mark these off, is going to be very similar. So I see that 72 inches long, and I see 36 inches wide this time, and 10 inches tall. So for that one, I get 25,920 cubic inches, which means the grand total volume is just the sum of those two. I got 46,656. So just add the two up, and that's the volume of your composite shape. And I think in general, the volume part's fairly straightforward. Surface area when you make composite shapes is the one that gets a little interesting because you might have to leave off the area where the two touch, which is just this little chunk right here. So as I go through, I'm going to erase this. I want to check out all the different faces. So let's look at this one. I don't know if you can see my highlighter very well on the purple. It is 72 by 24, and there are in fact two of those. So let's start surface area. I'm going to have 2 of the 72 by 24 inch faces. I will also have, what's this on the very end, 12 by 24, 2 of those, 2 times 12 times 24, but I will only have 1 of the very top edge, which is 72 by 12. All right, so that's that top box rectangular prism. Let's look at the bottom one. I see the front face is a 36 by 10, and there are 2 of those. There's a front and the back. So 2 times 36 times 10. The side, what is that, 72 by 10? There are 2 of those. I'm going to have to run onto a second line for this one. The trickiness, okay, so we got the front and the back, the 2 sides, the top and the bottom. The bottom is 36 by 72, but the top is not the same size. The top, we only want this little bit that's sticking out. Anything that ends up inside the shape is no longer part of the surface area. So we do have to do a little calculation to figure out that, what did we have here, 12 inches wide. 36 minus that 12 inches is really 24. So the top is really only 24 by 72. And you could even go combine that back in with the 2 times 74 times 24. You could make that a 3. We actually ended up with 3 of them. And I tried to type that all in very carefully and ended up with 11,376. This should all be in square inches. And again, you can either know that because we're getting area and that should be in square units. Or if you look back at each of our calculations, the 2's in the mix here are just saying that we have 2 of them, but everywhere else we're multiplying a length by a length, inches by inches. So we should get square inches across the board, which is a good thing because we can't add them up if they don't have the same units. And again, when I added them up, I got 11,376. I don't know if I'm 100% to be trusted on that, but I tried to be very careful. Okay, just one more to use some of the other formulas. We have a snow cone, which is a hemisphere on top of an inverted cone. Oh, this is going to make me go look up that formula I didn't give you. Serves me right. Let's see what we have to start with. We want to first find the volume of the snow. So that's going to be half of a sphere plus a cone. A sphere, we have formula 4/3 pi r cubed. And for a cone, it's 1/3 pi r squared h. And then I do need that 1/2 to stick around out in front. So basically that's my formula. So you can either go and do some side calculations and find both of those volumes and plug them back in here, or you can just go straight to mushing the formulas in here. I can simplify a tiny bit with that 1/2 times 4/3. That becomes 2/3. So I have 2/3 pi, the radius of the conical clip is 10 meters tall with a radius of 4 meters. The radius of the sphere is 4 centimeters. We're going to cube that. And then we need 1/3 pi, same radius, times the height, which was 10 centimeters. So these are a little more complicated just to make you think a little more than just plugging into a formula, but hopefully nothing too overwhelming. 4 cubed is 64, and we've also cubed the centimeters. 4 squared is 16, and that's going to be centimeters squared. I know I haven't been working with units in the formulas throughout, but it's sort of come into my memory that science teachers were asking about doing a little more of that as well, so I want to show you some of that. Okay, so I get 2/3 times 64. So 2 times 64 is 128 over 3 pi, and that's cubic centimeters. And then I have plus 1/3 times 16 times 10. So 16 times 10 is 160. Oops. 160 over 3 pi. And notice I just keep that pi hanging around, almost like it's units. It's not part of the units, but if I try and multiply in a 3.14, I'm rounding and I'm losing information. So this is sort of in the context of a word problem. I maybe wouldn't hate it too much, but I think for something like this, there's no reason that we need to round that unless we're asked to. Notice here we had square centimeters times centimeters, so we do end up with cubic centimeters again, which means the units match up. We can in fact add them. I need to find 160 plus 128 because everything else is common. They both have a common denominator. They both have the pi, so these are like terms. So I'm seeing 288, I believe, over 3 times pi cubic centimeters. So I think that's a fantastic answer. If you're asked for a decimal, plug that into a calculator. If you don't have a pi button, at that point you can use a 3.14. But otherwise, may as well keep it exact. That's an exact answer. It's perfect information, no rounding error. All right, this is the one that's going to make me go remind myself what the surface area of a cone is. And I found that the surface area for a cone, so feel free to add that back up top if you're taking notes, is pi r squared plus pi lr, where L is the length of the slant right here. So this is actually going to get a little bit tricky, and it's going to push us into a review topic that I actually saved for a little bit later, but I'll go ahead and start it now. I don't think you get any surface area of the cone questions in your homework, so this is, I think, safe for an example. The thing I really like about this is if we're trying to figure out how much paper was needed for the cup, that's this outside here. We don't want to include the circle on top. So even if that formula looks a little tricky, you do have to be able to analyze it enough to say, okay, but I don't want the pi r squared. That's the circle on top. So I really just want pi times L times R. And I'm going to do the work to find that out, even though, like I said, that's a review topic for, I think, next week. I don't think it'll hurt us to see it now so that I can do my example that I do think is kind of a neat one. So here's the deal. We actually have to make a two-dimensional problem to find that. So we know that the radius is 4 and the height is 10. And what I'm doing in here is making a green triangle, which happens to be a right triangle. So what we actually need to find that slant length is the Pythagorean theorem. So a squared plus b squared equals c squared. Again, we will review this a little bit more later on, but this is hopefully about what we need to be prompted to remember that it exists. The only thing really important here is that C has to represent the longest side, the hypotenuse, which in our picture is the L. It's always directly across from the right angle. It doesn't matter which leg, which side length, you call A and B. So we'll say 10 squared plus 4 squared, which is 116. So L, and again getting a little ahead, this is why I was saving it for later when we were doing this review, is the square root of 116. Which means the area of the paper needed to make the cone is pi times the square root of 116 times the radius. And the units on that would be inches squared. Again, oh, I'm sorry, was this inches? Centimeters squared for this one. And I'm just going to rewrite that a little bit. I'm going to say 4 pi root 116. It's not necessary to do that, but we generally write those square roots at the end just so that there's no chance of getting mixed up about whether the 4 is under the square root or not. Okay, so I think a little bit trickier than what you see in your homework, but it should still give you a good idea of how to approach. Thanks for watching.